So, welcome to episode 7 now of Absolutely Zero Knowledge. And I'm very, very pleased to be joined by Alin from Aptos Labs. So, Alan's going to be talking about his background in zero knowledge and what he's been working on currently. Do you want to give a very quick introduction and overview of yourself, Alin?
Sure, yeah. I'm a head of cryptography at Aptos Labs. I've been here for 2 years. I joined in 2022 February as part of the founding team. It's been an amazing journey. It's super, super fun to work at Aptos. I'm having the time of my life working with really smart people and on really hard problems. And for me, I was a researcher before joining Aptos, so what's really exciting is I get to work on, stuff that actually is used by people, and the stakes are very high. Money could be lost if we don't do our job well. So it's really, really exciting. Before Aptos, like I said, I was in industrial research at VMware, writing papers, giving talks, doing the academic game. And before that, I got my PhD at MIT. And before that, I was at a startup also in New York City with my undergraduate advisor. The startup was called Private Machines. We were building tamper-proof clouds. So we were doing basically something like Amazon, where not even Amazon can mess with your computation or snoop on it. Mm-hmm. So I've been very interested in security and cryptography for over a decade now, I guess.
And you were on the proper podcast, the ZK podcast with Anna Rose a little while ago when you were at VMware. So I was intrigued to know how.
Yeah,
you were obviously involved in research, like you just mentioned there, sort of the academic papers and research within zero knowledge proofs at VMware. So, I mean, very briefly, what specifically were you researching? What were you working on, and how were they harnessing zero knowledge there?
So I guess one really related project that we were working on right before I left for the last year was anonymous payments. Mm-hmm. So we were working on sensibly anonymous payments, to be more precise, because oftentimes when you deploy anonymity, it gets abused. Mm-hmm. So you want to deploy a payment system where reasonable people can transact anonymously, but malicious actors cannot abuse it. So we came up with this idea, which is not really our idea. It's an old idea from an old line of research, but we made it more efficient. And the idea goes as follows. We say we'll let you transact anonymously for the first, let's say, $5,000 you send per month. And after that amount, you have to clear your transactions with an auditor. So this is something that's meant to simulate cash transactions. So with cash, if your transaction amount kind of exceeds some ridiculous sum, it's kind of impossible to do it. You can't really give somebody $20 million easily, right?
Yeah.
But for small sums, it's very reasonable, and you maintain your privacy. Only you and the other person know how much was transferred, and nobody else even knows the transfer was made. So that was the spirit of the work. It was called Untraceable Transactions, UTT. And we use zero-knowledge proofs to hide the information, the sender, the recipient, and the amount. But we didn't use these general-purpose zero-knowledge proofs, so snark systems like Grot16, Blanc, Starks, etc. We actually used much simpler zero-knowledge proof systems, so something called Sigma protocols. So a Sigma protocol is a zero-knowledge proof system that only argues a certain relation holds between group elements in an algebraic group. Yeah. Now, this is a little bit of a technical lingo, but you can prove things like, hey, I know an element A and an element B, such that these other three elements are G to the A, G to the B, and G to the AB, let's say, stuff like that. And just from a snark for these types of arithmetic relations, you can build very efficient anonymous payments. And that was one line of work where we made a lot of heavy use of general purpose, zero knowledge proof systems, but not general purpose systems.
Yeah.
We also.
I was just going to ask quickly, was that predominantly on chain, or what were the specific use cases for that?
Yeah, so this was a system that you could deploy on an existing chain like Ethereum or Aptos.
Yeah.
by implementing it in a smart contract, like using Solidity or Move.
Hmm.
So that's totally doable. It would require you run a separate server, which we call the bank in our terminology. And this bank maintains a secret key and uses it to sign coins that it issues. Um, so in that sense, it wouldn't be fully autonomously running on chain. It would need a separate system as well, if that makes sense.
Hmm. Okay, cool.
Yeah.
And that obviously led you to Aptos then, and yeah, like you mentioned, part of the founding team. Are you able to share very quickly a brief overview of Aptos themselves, and yeah, what specifically they do in particular? Because I know you're not necessarily although you're using and harnessing a lot of zero knowledge technology, you're not, I don't know what we would describe, like a ZK house, like some others. So yeah,
Yeah.
I guess first of all, very brief overview of Aptos, and then how are you harnessing zero knowledge?
Yeah, so Aptos was started around, suppose November 2021 or something is when things really got going. Um, it's a layer one blockchain. It's a platform for smart contracts, proof of stake. It uses a new language called Move, which has very nice safety properties. So it avoids reentrancy attacks in languages like Solidity. And it's safely typed. And it also has the Move prover, so you can actually prove that certain properties hold on your smart contracts, which once again provides more safety. It's a high throughput, low latency blockchain, so we can reach thousands of transactions per second on mainnet in production, and latencies, sub-second latencies. Now, so that's sort of on the technical side. On the people side, Aptos was founded by Mo Shaikh and Avery Ching. They were at Facebook, and a lot of our team was from the original Diem/Libra/Calibra/Novi/ the many terms that people used. So those efforts came to a halt, and people there wanted to continue them. So they started Aptos Labs, and one of I think the first and second employees of Aptos Labs were two researcher friends of mine. So they told me about what they're doing, and I was very excited, and I joined. And that's kind of the story from my perspective.
Yeah, I mean, you mentioned there that it's sort of high volume, high throughput. I guess for your use cases, does that mean you're angling more towards the sort of privacy and security element as opposed to the scalability factor that you might see from the ZK EVMs that we all know? If the blockchain, I guess, already is fairly scalable by the sounds of things. So yeah, are you more on the sort of privacy security side?
By we, you mean Aptos?
Yeah, yeah.
I actually think it's flipped in a way. Not that we're not doing things on the security front. We are for sure. We're very mindful about security. We use Rust. We developed Move as a safe language, and not that we're not doing things in privacy. So we do have support for many privacy things on Aptos. For example, we have something called veiled coins, which allows you to add a thin layer of privacy to your transactions and hide the amounts in the transaction. But we're definitely, I think, much bigger on scalability than other folks. You mentioned sort of this idea that folks are hoping to scale cryptocurrencies using ZK snarks, right? Yeah, so that's actually an area I want to spend more time to understand what folks are thinking, because to me that approach doesn't immediately pass muster, just because of the fact that a ZK snark system has an incredibly high proving time. So what that means is that when you want to prove a block of a large number of transactions, you have to wait hours, right, or minutes. And if you don't want to wait hours and wait minutes, you have to throw a lot of CPU power at it. So it ends up being more expensive too. And even if you wait minutes, the problem is that's still hundreds of times slower than the 1 or 2 second latency that a network like Aptos has, right? Using just BFT consensus. So you're sacrificing something. You're sacrificing latency, confirmation latency, like that point where you really know your transaction is in consensus, has been executed, the results have been applied, and you can rely on it In other words, like if you're buying a Lamborghini from me and you're sending a transaction into a ZK rollup, right? You have to kind of trust these sequencers that kind of promise you that eventually they'll prove this transaction and include it in a block in the layer 1, right? And it's actually, I have to trust it if I'm going to give you the Lamborghini, because if I give you the Lamborghini without seeing this confirmation, maybe your transaction never makes it and I never get your money, right? But you got my Lamborghini.
Yeah.
Right. So I think latency is very important for some use cases. I also think it's not important for all use cases, and maybe that's part of what I'm missing as a researcher. I didn't have enough chance to look into why people think this approach will actually lead to anything, because the latency will be very high as far as I can tell.
Yeah.
And developments in ZK snark systems are, moving very fast and they're really exciting. But at the end of the day, it's really hard to imagine how you'll be able to get to within like 100x or even 10x of normal execution time, right? So yeah, latency seems to inherently suffer in the system, and that I think affects use cases and in turn affects scalability. Nonetheless, it's a very exciting direction, and I'm sure people will come up with tons of creative ideas to get around this this limitation. Yeah. But to answer your original question, we're very big on scalability, and we're working really hard on increasing throughput while maintaining low latency. It's actually important to do both, because it's really hard. It's really easy to get 10,000 transactions per second if your confirmation time is 20 years.
So of course.
it's important to keep the latency low.
Cool. And I mean, ask the question for that sort of purpose, that when I've said numerous times, when I first trying to get my head around zero knowledge, I could totally understand the impact that it can have on sort of security and privacy aspects. But when I learned that so many use cases for it actually are sort of to increase scalability, that it was certainly something new to me, and just shows as well for you at Aptos Labs, certainly thinking about that too. Cool. And
it's a natural property of zero knowledge proof systems. So they give you succinct verification, so they help you reduce verification time, but they also give you succinct proof size, so they help you save communication, and that naturally leads to scalable solutions in many applications.
Cool. And one of those examples you just gave us was around sort of veiled coins. I know that's something that it's quite significant, or a significant project that you've been working on fairly recently, and something you've been, are you able to share a bit more detail about the sort of that use case in particular?
Yeah, that was a very early exploration that I think I started in September 2021, and our cryptography engineer Michael Straka saw it to the end in the second year, 2022. It was basically trying to ask the question, what can we do for privacy in Move, in our smart contract language? For example, could we add a thin layer of privacy to any coin created in Move? So just like in Ethereum, you have ERC20 as a token standard, and you can create your own token, your own coin. We have a similar thing in Aptos. It's just called the Aptos coin standard. And I was curious to see if it's possible to add a generic layer of privacy for any type of coin, right? And that's what the Veiled Coin project was about. The idea was to just hide the balance and the amount. And the solution is well known. It's not novel research in any sense of the word. It's just a tech transfer of existing research while handling production constraints of the Aptos system. So what we do is we encrypt the balances using something called additively homomorphic encryption, and we encrypt the amounts using the same scheme. And then we prove, for example, that if you have an encrypted balance here and I have an encrypted balance here, and you're trying to send me an encrypted coin amount, we're proving that what you withdrew from here is not greater than what you had encrypted. So let's say if you have 10 encrypted coins, you're not transferring 20, right? So we're proving that the encrypted transferred amount is smaller than the source balance, right? And then because of the homomorphism property, we can take this encrypted amount, which is the ciphertext, subtract it from the source, and add it into the destination, all without revealing the amount. This is basically all cryptography relies on these so-called homomorphisms.
Yeah, and I spoke to Jason from Zama, and obviously they're working significantly on fully homomorphic encryption. But yeah, I guess both those use cases, or that use case you mentioned there for FHE and ZKP as well, it seems like almost the most simplistic use case in particular, and one that you could almost transfer so easily into the world of Web 2 and banking and fintech. Showing that you have enough monies to make that particular transfer without needing to reveal anything else around that. So is that something that you see being used more widely, I guess, in Web 3, but also Web 2?
This sort of privacy layer on top of coins and cryptocurrencies. Well, in my sort of, let's say uninformed and limited opinion, I don't know everything and I can't foresee the future. As far as I can tell, it's hard to imagine how blockchains will take off without privacy. People are really not comfortable with others observing their transaction history and their full balances. And it's not that they're just not comfortable, it's also a kind of a big risk for you. Like if I know how much money you have on chain, I can target you, right? And cryptocurrency people are already targeted when they land at airport in person, right? Like this is real stuff that happens. So from that point of view, I think it's very important. On the other hand, if you don't take care of, let's say, accountability or auditability or sensibility, just make an anonymous payment system that's reasonable, that's sensible, so that regulators are pleased also, and your system isn't abused for nefarious purposes, which it can be, privacy is not going to take off either. So that's where I think the really interesting research lies. That's why we kind of worked on UTT, and we're hoping to do more stuff there. So for example, with UTT, I mentioned that we needed this separate server that maintains a secret key. I didn't get a chance to mention that if that secret key is compromised, then everybody can create coin out of thin air, which would be very bad. So we're working on actually eliminating that secret key and that server and addressing that point of failure. But yeah, I think the answer is absolutely. We need privacy, but we need regulation too. We need reasonableness, let's say, sensibility.
Yeah. And is that linked into sort of fully anonymous payments? I mean, you mentioned what you worked on at VMware, and I think you're doing something similar. Are you at Aptos in terms of anonymous payments? I guess that's making the user anonymous as opposed to encrypting the transaction. But you're working on something like that, and can the two work hand in hand?
So beyond veiled coins, we have not done more privacy-preserving payments work at Aptos. Like I said, there's sort of a technical challenge of doing it efficiently and accountably. You can use ZK snarks, general purpose ZK snark system like Zcash, for example. It's easy to add accountability into them. But then, there's a big implementation complexity associated with general purpose ZK snarks. That would be one solution. And I think a more complicated logistic with accountable anonymous payment system is you need sort of a regulator or a trusted entity that is able to look at transactions, and who can that be actually? Who is such a reasonable entity? Because people trust different entities.
Yeah, I think the governance and the regulatory aspect is something that I'm always keen to sort of understand and try and figure out, because if you are encrypting values and anonymizing data, then what's to prevent someone using ill-gotten gains to make particular transactions, for example. And obviously there are regulators in place, but I guess that's a challenge in itself. Is that something that you've had to figure out, or have you come across in at Aptos?
No. I think what I find sort of fascinating is if in some of these accountable anonymous payment schemes, it's very easy to designate one trusted entity that can decrypt everything, right? I think the next step in research is to figure out how to actually audit this entity too. So the entity is auditing the anonymous payments, but now the users of the system should be able to audit the entity too, because the entity can abuse its power, right? So it can look at too much information, right? So you actually want some transparency. Like you actually, for example, might want statistics. How many payments has this entity revealed this year? How many accounts has it looked at? What's the volume of transactions that it looked at? Stuff of that nature. I think that would be very interesting, because then people might feel more comfortable with sensible anonymity, with accountability in their anonymous payment systems. But we haven't had a chance to work on that too much yet.
You mentioned there sensible anonymity.
A speck of an idea.
Okay. Yeah, you mentioned that. Is that? Well, can you share more about that? And once again, something you're working on.
So actually, this is what I mentioned earlier, the UTT line of work. I actually gave a talk on it at the Stanford conference, Stanford Blockchain Conference earlier last summer. It's a 20-minute talk. It's up on my YouTube channel. It's also up on the Stanford Blockchain Conference channel. So that would be a good resource for you and folks to follow up, or I can give you the link later if you want. And then, like I said before, what in that work, what we believe is sensible would be to just limit the monthly anonymous amount that is sent out of an account. I think it's sort of hard to, in my mind, it's sort of hard to argue that the abuse in such a system would be so bad that it's not worth having. But, obviously other people might disagree, and an interesting debate should be held, I think.
Cool. And I mean, in terms of all these use cases, how are you selecting the right tools for the job? That might sound like a really broad and dark question, but maybe somewhere like Aptos, where you're building out a blockchain, and like I said at the start, you're not necessarily a ZK house using zero knowledge all day, every day. And why zero knowledge? How do you find sort of tackling the complexities of ZKP?
Great. No, I think that's a nice question. Actually, to avoid speaking in broad general terms, which can be confusing for people, I'll actually give an examples. So actually, in the past, let's say 4 months plus, we've been quite a ZK house, because we've been working on this project that let's call it keyless blockchain accounts. So the idea is to leverage an existing Web2 account, like your Google account or your GitHub account or your Microsoft account, as a blockchain account. So instead of having a secret key and a mnemonic, which is very easy to lose, you have your existing Web2 account, and more or less you sign transactions using that account. In fact, what's actually happening is you're getting the provider, which is Google or GitHub, to sign your transactions for you. And in order to make this approach work with privacy, you have to use zero knowledge proofs. If you don't want privacy, you don't need zero knowledge proofs. You can just throw some signatures from Google on chain and reveal the user's email address, and that's it. It works fine. You still get everything you want in terms of functionality. No more secret keys. Really easy to onboard users. They just have to sign in with Google, like in a website like Notion, for example. But if you want privacy, you want to hide that email address, and that's where you need to use your knowledge proofs. So anyway, so that's some context for the problem setting. Now, how do we pick the tools you asked? And the way we do it, and I think the way everyone else do it, is they look at their system and at the constraints that they have. So in our case, because we want to provide privacy, instead of verifying the signature from Google on chain, we have to verify a zero knowledge proof of knowledge of such a signature from Google on a particularly formatted message with certain properties in very big, broad terms. But still, at the end of the day, we're verifying a zero knowledge proof on chain. So that means that the verification time has to be really small, because if it's very big, you have a denial of service problem. An attacker could craft a transaction using an invalid zero knowledge proof, and your network has to verify it in order to dismiss it, right? So if verification takes, let's say, a second per proof, an attacker can craft 60 transactions and waste 60 seconds of CPU time, right? So you definitely want really low verification time. And that's probably like the top concern. It's just verification time. And now you have to look for snarks that have really small verification time. Another constraint that you have is proof size. Because each transaction comes with a zero knowledge proof in order for the chain to verify it, it's very important that the proof not be 1 megabyte or hundreds of kilobytes, like in a Stark, for example.
Yeah.
Right? So obviously you want something with a small proof size too. And another constraint that you have is, well, when users are signing their transactions, sometimes they're going to be computing these zero knowledge proofs. If you do it right, it's only when they sign in, and then later on it's very easy. But still, when they sign in, you kind of have to compute a zero knowledge proof. And you can't be wasting like 2 hours computing this proof. It has to be fast because the user won't be able to transact for 2 hours until it has the proof. So you need a proof system with fast proof time. And lastly, like all of this stuff has to be upgradable. So let's say you define your zero knowledge relation, if you're familiar with that terminology, over which the proof is made. So for those listening, what is a zero knowledge proof system? A zero knowledge proof system for a relation R proves that for some public input X, there exists a secret input W such that the relation R holds on these two inputs X and W. That's the only thing that it does, right? So there's a relation R that encodes this verification of the Google signature over the right message with the right properties. But this relation R might change in the future because we have new features. Or maybe we had a bug in our relation because everybody makes mistakes. So the R might change into an R prime, and then you have to update your system. And for some snarks, this is hard to do because they have something that's called a trusted setup. So every time you fix a relation R and you want to compute a proof for it, you have to do a trusted setup specific to that R, output a proving key, and only then can you prove with respect to that proving key for the relation R. And if R changes to R prime, you need to recompute a new proving. And actually, this is made even more difficult by the fact that in systems like ROT16, the proving key cannot be computed by a single party, because that single party has access to some secret information when it computes this proving key, and that secret information allows it to forge proofs. So that would be very bad. So instead, what you do is you do an entire multi-party computation protocol where you add in a bunch of participants to generate this proving key jointly so that no single participant gets access to the secret information. So all of these are kind of constraints about how you think about your toolbox. So you start from the system constraints, small verification time, small proof size, fast prover time. Maybe we don't want the trusted setup, or maybe we'll take one, deal with it, and figure out how to do this MPC ceremony really fast. So I hope that was kind of a long answer, but I hope that sort of answers, that gives you a concrete example of how we thought about it.
No, that's perfect. And obviously I have so many conversations all the time now about zero knowledge proof, and obviously when I'm not from a technical background from in any way, shape or form, but yeah, it's just so obvious now to me, and it probably should have been at the start. But zero knowledge isn't just a tool you can use in any scenario. Actually, you do need to obviously give some thorough thought to the problem, how you want to solve the problem, and then ultimately use the right tool for the job, whether that is zero knowledge, whether it's MPC, FHE, and I guess the different sub-varieties of each for those. But yeah, I guess it all comes from the problem you're trying to solve, right? And it's not just let's use a zero knowledge instead of MPC, because they're actually incredibly different and have very different qualities and ultimately use cases, I guess. You touched upon a little bit there about sort of what you've been working on significantly over the last 4 or 5 months. Is there anything else you want to touch upon, the sort of around those keyless blockchain accounts, or where that idea was birthed from, what the issue is you're trying to solve, who's going to use it, anything else you want to share?
Yeah, sure. We're really excited about this project. So you asked where the idea was birthed. So it kind of started last year. Around February, we're thinking about how to eliminate secret keys from our users, because I don't know, I presume you've tried to manage your own secret key and you know how much of a pain it is.
Yeah.
And a natural solution is to use an MPC system if you are familiar with this approach.
Yeah.
So the idea is you have n servers, and these n servers will manage your key for you. The key is actually secret shared amongst the n servers, so that let's say 50% or more can reconstruct it, but no less can, right? So you put this key on this MPC servers, and the MPC servers will sign on your behalf. But a natural question arises when you do that, right? How will the MPC servers know who you are? Because if I can trick the MPC servers into getting me a signature using your key, that would clearly be very bad. So now you've turned the problem of managing your own secret key into a different problem, which is authenticating yourself to an MPC system, right? And when you think about how to solve that problem, which is what we were doing in February, we came up with two solutions. One solution was to use this new standard for signatures, public key cryptography and signatures in the web called passkeys. And that standard is very exciting, and we can talk about that separately as well. We're doing work in that domain too. But at the end of the day, it's not sufficiently mature yet, and it's not seen sufficient adoption yet. But I think in 2 years or maybe less, it's going to be all over the place. But to keep the story short, passkeys were not ideal for this. The other approach was to use OAuth or OpenID, which you're familiar. Every time you go on a website and it asks you to sign in with Google, it's showing you this prompt, and it's using a protocol called OAuth/OpenID. And when we thought about that, we realized, well, if you sign in with Google on a website like notion.so, what happens is Google actually signs a message for you after you successfully logged in and sends it to notion.so. So notion.so now has a signature from Google, and the signature is actually over your email address and some arbitrary information that you get to include in there. And at some point in April 2023, I was sitting in my office and thinking about this a little bit. I'm like, okay, so this MPC servers can get this OpenID signature and verify that I am this Gmail user with this email address. Then why the hell do I need the MPC system for? I can just put the signature directly on chain, and the blockchain can verify that I am a certain user with a certain email address, right? I don't need the MPC system. And that's how this project was born in April 2023. And then we kept thinking about the security implication of the OAuth protocol and the OpenID protocol, and how to keep that safe for our users. Yeah, so that was kind of an interesting project. So for a long time, we actually thought the approach is not going to be secure. We had a lot of concerns about OAuth. But in the end, somebody in our team knocked some sense into us, and we moved forward.
Cool. And you mentioned, you mentioned the whole way through, and like I said, you're touching upon a load of different cryptographic primitives. It's not just the ZK drum that you're banging. There's MPC, homomorphic encryption. Is there anything else you want to share about, what sort of cryptography tools you're using, or you mentioned passkeys just then, but anything else you're working on at the moment that you can touch upon?
Yeah, sure. So this is very mildly related to zero knowledge, and I'll tell you how. But one exciting direction we're working on is on-chain instant randomness. So we're trying to give our Move smart contracts a very simple API that they can use to get randomness. And this will allow you to do things like games, lotteries, raffles, and it even has applications for zero-knowledge proof systems, because in zero-knowledge proof system, the verifier can be interactive and needs to pick randomness in order to verify a proof and interact with the prover. And interactive zero-knowledge proof systems are typically never used on-chain. You always use non-interactive proof systems on-chain, precisely because you don't have randomness, and usually also because you want to avoid interactions. So we're kind of excited by how maybe this on-chain randomness that we actually just deployed in a separate network will be potentially leading to interesting use cases in the zero-knowledge space because of this interactive verifiers that are now possible. Yeah, so on the on-chain randomness front, there's a lot of cryptography there. It's pretty hard to get that approach to work. We use something called publicly verifiable secret sharing, where you have a dealer that has a secret, and it wants to share it within participants such that any, 50% can reconstruct it, but no less can. And one of the things that the dealer has to do is actually prove knowledge of the secret, but do so in zero knowledge, which means that the dealer picks a secret and then creates a commitment to that secret. Let's say picks a secret A and commits to it as SHA-256 of A concatenated with some randomness, as a dumb example. And then given that commitment, if I give you that hash as the dealer, I now have to prove to you that I know this A under this hash, right? But I don't want to reveal to you the A, and I don't want to reveal to you the randomness R either that I hashed A with. So what do? I do a zero knowledge proof of knowledge of a secret A such that this hash is equal to SHA of A concatenated with R, right? So this is a very key security ingredient of verifiable secret sharing protocols, right? So our approach uses zero knowledge proof in that sense in a very limited scope. And yeah, we do PVSS. Each validator shares a secret. All of the other validators do the same. You figure out which validators dealt correctly, and then you take all of their secrets, multiply them together. That defines a sort of validator set secret for all of the validators that 50% or more can reconstruct. And now the good news is that once the validators have the secret, they can generate randomness from the secret very fast per block. Like for every block, they can put a piece of randomness in the block. And then smart contracts can derive their own randomness from that block randomness. But even there's challenges because generating randomness per block fast is kind of tricky. The secret sharing that I mentioned earlier is rather expensive. So we do some cool cryptography there too. I wouldn't say we use zero knowledge proofs there. We use something called a weighted verifiable unpredictable function. And we have a very nice optimization that allows us to reduce the communication complexity involved in aggregating this weighted verifiable unpredictable function every time we compute the randomness for a block. And that's all I'll say, because otherwise the details get very hairy very fast.
Well, I appreciate
but that's a very exciting line of work for us.
Yeah, I appreciate you sharing. You've shared so many diverse examples of how you're utilizing zero knowledge, and I guess just in general shows well the diversity exactly of the primitive itself. But is there anything else you want to potentially share, or anything that you're working on or have plans to work on in the future, or maybe even more broadly? Might be two separate questions, but where do you see the future use cases or the potential of zero knowledge going?
I see.
That's a very broad question, I know, but you fire away.
Yeah. So let me. Okay, good. I think I can answer that once again from the perspective of what we're working on, and I'll generalize from that. So we mentioned these keyless accounts, right, that are used Google account. And one of the biggest problems we see is the high proving time associated with using a snark like RAT16. Even though you can get the proving time to be under 1 second on a big machine, like a 32-core machine, it's still a problem because we need a deployment to compute these proofs. The users can't compute it themselves in the browsers. They would need 20 seconds to compute them, right? So that's very unfortunate. And there's many things you can do. You can play with different snarks and see what they might give you in terms of the proving time, and you can play with the implementation of the zero knowledge relation and optimizing it. You can use lookup tables. You can use all sorts of crazy tools. And we have a lot of ideas there. I'm not going to go into details since it gets, once again, hairy very fast. But to answer the second part of your question, I think obviously you see this now, that the most important direction that people are working on is reducing proving time. They're working really hard on reducing proving time. And part of the reason they're doing this is because if you think about proof size, you can usually reduce proof size via recursion. You can apply recursion to reduce the proof size, but proving time is still a bottleneck. So there's a lot of exciting developments there. Folding techniques, incrementally verifiable computation, these snarks that are very tailored for powers of 2, like Plonky 2, and I think this new line of work called Binius, if I remember the name correctly. And then works like Lasso and Jolt. a lot of cool developments and very, very exciting. It's really hard to keep up with all of it. So that's one thing. Another thing that I think is going to be important is to get rid of the trusted setup in snarks with fast prover times. Trusted setups are very hard to pull off. They require coordination. They require extra participants. So all of this is a problem. In the general space of what people will do with zero knowledge, I see a lot of excitement about ZKML stuff. I don't know what to make of it. Once again, I come back down to the high proving times, which would make machine learning so much more expensive. It's hard to imagine how that could ever be done practically. I see excitement about rollups, but once again, I see problems with the high latency. And again, all of these come down to the high proving time. And there's some new developments in identity. So the line of work that we're doing, I think other projects have done the same. We actually, like, if you go in our Aptos improvement proposal for this approach, we cite a bunch of works that have taken this direction as well. I think in that direction is quite likely to be very applicable. I've seen even some folks doing zero knowledge proofs that you have a US passport, because your US passport actually has a digital signature on it from the US government. Yeah. So you can now prove knowledge of such a signature, right? There were some folks that I met last year in April, I think. They were working on this. I wish I remembered their name so we could do a plug for them, but yeah. I don't. So I would say in identity, it's very exciting to see what's going to happen in identity. I mean, I'm curious to see what you think, actually. What do you think is...
Well, it's interesting. I think exactly what you mentioned. I think I virtually don't have a conversation now with, a technical person like yourself who doesn't make some sort of mention about just increasing the efficiency, the latency, the proving time, etc. And I think you couple that with the just massive increase in demand for zero knowledge proofs, that, those two things hand in hand, that there is, like you mentioned, a bottleneck and a real challenge around that. So whether that comes from, a proving programming language, whether it's a ZKP marketplace, whether it's making them more portable, but virtually, every conversation I'm having at the moment is around that, and therefore I think you're seeing quite a lot of startups. We work with people in the developer tooling for zero knowledge, so it seems like almost like virtually half the startups now in the space, that might be an exaggeration, but so many are now already coming up with challenges to exactly what you described about just increasing the efficiency, decreasing the cost of proving. So I think that will be a massive area of growth, which is crazy to say, I guess, already, that it just shows, like I mentioned, the increase in demand, the increase in popularity of zero knowledge already means that we need to have a think about how we can improve the efficiency. So that would be something I've definitely noticed too.
Mm-hmm. I think there's two other things that come to mind too that you see a lot of work on these days, which is these bridges that are typically secured via multi-signatures, which often get hacked because there's 4 or 5 servers out there whose keys get compromised. A lot of folks are excited about transitioning them to zero-knowledge-based bridges, where you prove you don't actually need the zero-knowledge part because everything is public. You just need the succinctness. We can prove things about the state of another blockchain, and we can verify that proof onto a different blockchain. Mm-hmm. So that's one exciting direction. I think Wormhole recently announced a partnership with Alin Labs, and they're going to work on a ZK bridge for Aptos and some other cryptocurrencies. Okay. So there's a lot of excitement there. Once again, I hope the proving times are going to be reasonable. Lurk Lab is doing some interesting work using Nova, and they actually have a very nice domain-specific language that is Lisp-based to specify relations. So that's kind of, I hope, going to be much safer to use than existing languages like CirComp, for example, which I guess brings me to my other point. I hope that a lot of work will be done on safer domain-specific languages for specifying ZK relations. We, for ourselves, have had a kind of an awful time using CIRCOM. I mean, obviously, hats off to ident3 and the people who built it. It's good to have it, to have such a tool to begin with, but it's kind of very unsettling to use. It's very easy to make mistakes. So when you look at more mature, like safer languages like Rust, for example, that you could use to specify a ZK relation, that's really exciting. And I think folks at RISC-0 are pioneering that approach. And more, and even I think folks at OSTEC have this language called Noir, which is supposed to be safer. And that's going to make a ton of difference for developers, because right now, very few people can write CIRCOM. You need to understand a lot of things. Like in CIRCOM, you cannot multiply A times B times C. You have to do A times B is equal X, and then you have to do X times C is equal Y, because it only supports quadratic relations. It's very tied to the representation of the relation that the snark actually proves. So that has a lot of implications for how easy the code it is to read, how easy it is to audit, how easy it is to make mistakes. So I hope a lot more work will be done there, and I think it'll make a huge difference.
Oh, well, I think we've touched on everything I was keen to do so, and I really appreciate your time and running me through a lot of what you've been working on at Aptos, but also your thoughts and feelings of what we might see pretty soon. Just before I leave you, is there any final words of wisdom you would like to provide to someone who is potentially looking to get their foot in the door within zero knowledge? Something I'm always keen to ask, but from yourself, who's working, probably hiring people, working at the sort of C-suite level, what advice would you give to someone trying to enter?
I kind of took the academic path. That's how I got into it. But I think a lot of folks these days, that they're not going to be taking that path. They're going to go on some GitHub repo and find a bunch of resources and start playing with it. So just the general advice is to get your hands dirty quickly and see what you can do. There's, I think, great resources to speed up fast. Like there's this awesome ZK GitHub repo that has a lot of resources. And there's a newsletter that I follow called ZK Mesh. You might be following it as well.
Yeah, I do.
Which lists a bunch of academic results, and it's a very good mix of academia, industry, blogs, funding, events. So everything that is happening you can get from this monthly newsletter. And it's going to be overwhelming when you first look at it, but what isn't in our space, everything is quite complex until you start distilling it down. But I think it's a good way to get your hands dirty.
Yeah, I think that's been the general advice, I think, to not be afraid and just to get stuck in and ultimately just give it a go. So I'll include some resources. I'll include some of the things we mentioned. Your talk at it was SPC, wasn't it? I'll share that as well. But yeah, I very much appreciate your time. Thank you very much for that.
Thank you, Ed.
Unless there's anything else, I will leave you be, and yeah, we'll stay in touch and speak soon.
No, yeah, thanks for having me, and really, really exciting that you're doing this podcast line. I hope you get to educate the public more on what this technology is and what it can do. And really grateful to be on. Thank you.
That's all right. Thank you so much for your time. I really appreciate it. We'll speak soon, Alan.
Cheers.
Bye.